Welcome to another installment of Organic Chemistry with Kenny Miller. I'm your host, Kenny Miller. Today, we'll be talking about the final portion of how alcohols react, specifically other reactions of alcohols that we haven't discussed yet, mostly substitution kinds of reactions. Okay. So in some cases, you're already familiar with these reactions. If you remember back to previous semester, if you have an alcohol, like a tertiary alcohol such as this one, and some acid, let's say, with a nucleophilic counterion like HBr is a good example. OH by itself is not a good leaving group, so we need to turn this bad leaving group into a good one. We can do that by protonating the oxygen, which releases a bromide ion. So the result here is that we've changed a bad leaving group into a good one. And now this leaving group can leave. This can only happen with secondary and pretty much tertiary substrates because notice that what we're going to do is generate a carbocation intermediate, right? This one is tertiary, so it's reasonably stable, at least for carbocation. And now the bromide that we released in the first step can attack that carbocation to give us the product of substitution here. Note this is an SN1 reaction overall because the rate determining step is this leaving group leaving. We get a quick nucleophilic attack to generate a new carbon-halogen bond. We release water in this step, which is also a byproduct of the reaction. So just refresh your memory on SN1 reactions of alcohols. We've learned these previously. These take place through an SN1 pathway only if you have a secondary or tertiary alcohol. So what if you want a halide of a primary alcohol? Before we go there, one other thing that I wanted to mention is that historically and actually in more modern times, what we do is actually a two-step sequence that allows us to turn the oxygen, the OH group, into a good leaving group called a tosylate. And then we can displace that tosylate with any nucleophile that we want. So tosyl chloride actually looks like this. It's toluene sulfonyl chloride. So all this crap is abbreviated TS. And then when we attach this to an oxygen, what we get is an OTS, which is now a good leaving group. So we've taken, just like in the previous case, by protonating the OH group, we get a good leaving group. By tosylating the OH group, we also get a good leaving group. We add pyridine as a base, which removes this hydrogen. And so, for example, let's say that we took this alcohol and treat it with tosyl chloride and pyridine, and we get the tosylate that's shown above. Now we can displace this leaving group with any kind of nucleophile that we want. Let's say cyanide. Notice that since this is an SN2 reaction now, this is a good leaving group, that we're going to get inversion of configuration. Or you can have the thiolate ion. Any of the different nucleophiles that we've already talked about, good nucleophiles that are weak bases, are going to be perfect for these kinds of SN2 reactions. The advantage to tosylates is that these compounds are isolable. So we can make it, isolate it, put it in a bottle, store it, and then use it at a later date. Okay. What if we want to make a halide from a primary alcohol? Now we have a primary alcohol. SN1 pathway is not possible. But again, what we need to do is turn this into a good leaving group. So one possibility is what I just showed on the previous slide. We could make this into a tosylate and then displace that tosylate with chloride ion or bromide ion, but that would be two steps. In this case, what we can do is, in one step, transform these compounds directly from an alcohol to a chloride or from an alcohol to a bromide. And the pattern is going to be exactly the same. What we're going to be doing is taking a bad leaving group, turning it into a good leaving group, but just in the same reaction, then displacing it with a chloride ion. So let's talk about the mechanism on the next slide. So let's say you have a primary alcohol like the one I showed on the previous slide. You have a primary alcohol, but this could happen with primary, secondary, and actually even tertiary alcohols. You have a primary alcohol. We treat this with thionyl chloride, SOCl2. Here's a Lewis dot structure. So the first step is this sulfur atom is really electron poor because it's bonded to an electronegative oxygen and two electronegative chlorines. We have a lone pair of electrons that can attack that sulfur and at the same time break the sulfur-oxygen double bond. So we get a sulfur-oxygen single bond. The sulfur is still bonded to two chlorine atoms. So we have a negative formal charge on this oxygen. We have a positive formal charge on this oxygen. The sulfur-oxygen double bond is pretty strong, so we can reform that sulfur-oxygen double bond, and chloride is a good leaving group, so the chloride leaves, and so what we get here something that looks like this. We add pyridine to the reaction as a base. Okay, it has a lone pair of electrons that can pull off this acidic hydrogen. Okay, so now what we have, the point of all of this is to get to this point, right? Because now what we've done is we've taken a bad leaving group, we've turned it into a good leaving group. We generated a chloride ion in this step. So now what can happen is the Cl- that we generated in this step when the Cl- left, now that can act as a nucleophile. We have a primary compound with a good leaving group, SN2 reaction. We can kick that off. And we get a chloride. So the net result here is we've gone from a primary alcohol to a primary chloride. We also have a good leaving group, so we have a O, S, double bond O, Cl. This is resonance stabilized. And this can also continue to react to give sulfur dioxide gas plus chloride ion, and this chloride ion could also participate in another SN2 reaction. The mechanism for formation of a bromide is actually a little bit more straightforward, but the theme is exactly the same, right? We have a bad leaving group, our OH group, we want to turn it into a good leaving group. So what happens? This phosphorus is very electron poor, it's bonded to 3 bromines. So the lone pair of electrons on oxygen attacks the phosphorus, bromine leaves. We get this thing, which is a good leaving group. Why is this a good leaving group? Because when it leaves, it forms a neutral compound, right? Just like the reason why water is a good leaving group, because it's positively charged. When it leaves, water is neutral. It's a weak base, right? So the bromide that we released in this step can come back in, attack the carbon in an SN2 reaction to generate an alkyl primary alkyl bromide and our leaving group. So be familiar with both of these mechanisms. Some other reactions of alcohols that we've already talked about. One is the E1, dehydration of an alcohol. Remember that if you have some strong acid, I'll just represent this in its Lewis dot structure. Remember the mechanism for this, right, is that again we're going to take a bad leaving group, turn it into a good leaving group by protonating it just like we did earlier. So now that can leave to give us a tertiary carbocation, right? There's no nucleophile present though, so we can't do a substitution reaction because this leaving group is non-nucleophilic, but it can act as a base. So we can pull off this hydrogen and form our double bond to get the product of E1 dehydration of an alcohol. So that's another possibility. That's another thing that you can do with alcohols. And the last reaction that I'll talk about is an E2 elimination, right? Which we're not necessarily, we remember E2 reactions, right? If we have a good leaving group here, we can treat this with a strong base and then get our alkene, but this is not a good leaving group, so instead what we're going to do is tosylate. That's going to give us a good leaving group. And then treatment with a strong base. Remember, the mechanism of an E2 reaction is that we pull off the hydrogen, we form the double bond, the leaving group leaves all in one step, which gets us to our elimination product. Okay, so to summarize, this is pretty straightforward. Many of these reactions we've already talked about. We've already talked about SN2 reactions, E1 and E2 reactions. It's just that in some cases we're forming leaving groups that we haven't seen before. So familiarize yourself with the mechanisms, especially the mechanism of conversion of an alcohol to a chloride with SOCl2, the conversion of an alcohol to a bromide with PBr3, and we'll talk about how we can use these compounds in a later video.